Hello everyone, I hope you had a nice vacation. Okay, and it's very relaxed and you're back and ready to go back and learn some advanced data science. Today we will be talking back where we stopped last time in gradient descent. Okay, and then we'll be talking a little bit about derivatives and computational graph. Um, so let me recap of what we did last time. Last time we took an example of logistic regression, cost function, and we calculate the loss function to minimize the error between the predicted results with the actual results. And so we knew that the loss function is applied for a single training example, while the cost function is the cost of the entire training set. And we wanted to do this to minimize the overall cost. So akid we want the difference between the predicted and the actual results to be as close as possible, because this will show that how accurate our results are. That's why we use something also called gradient descent, and we will talk deeply about gradient descent today and how we can use it and how to train and learn the parameters on your training set. So today I'll be talking deeply in by the end of today, you will know what is gradient descent, you'll know how it works and why do we use it and why is it essential really to always optimize our models. So to recap, here is the algorithm, the logistic regression algorithm. Okay, so we have it over here. Okay, and on the second line, we have the cost function over here. And the cost function, as we said, it has W and B, and it's defined as the average. So it's 1 over M. You can see here 1 over M. Okay, the sum of the loss function. So it takes all of the loss function, it sums all of the loss function that we have done on the entire training set, and M is the how big the training set is. Okay, and here's the loss function. Okay, and so the loss function measures how well your algorithm outputs y hat. You can see here y hat, and on each of the training example it stacks up compared to the ground truth label. نحن عرفنا the ground truth label is called yi. Yi is for the instance, the ith iteration, but when we do it here, it is for all of the actual truth values. So we stack them all together, we add them all together, and then we compare them with, we get the result of what's the difference between predicted and uh, the actual. And here you can see here is the expanded the formula. So when we want to apply the formula, it's over here. So the cost function measures how well your parameters W and B are doing on the training set. And so in order to learn a set of parameters W and B, it seems natural that we want to find W and B to make the cost function J of W as small as possible. So again, why do we need to make this as small as possible? Okay, because we want the difference between y hat, okay, and yi to be as as small as possible. يعني إذا نحن عملنا prediction طلعت 5, okay, and the truth value is 6, the difference is 1. When we want to find the cost function حيقلنا هيدا 1. We want the number to be as small as possible. أكيد مثلا إذا كانت 10 this is يعني هاي بتصير شو اسمه هون. Let's say this is 15, okay, وهون it's 16, so sorry, هون it's 6, so it's here 11, and this is of course a worse cost function. So now that's why بنخلي the number between y hat and yi as small as possible. And so here is the illustration of the gradient descent. This is how a gradient descent looks like. We have a lot of different diagrams. But this is one of the diagrams that we're going to represent. And the space parameters عندنا W وعندنا B. Okay. And the cost function J is some surface above the horizontal axis. Okay. So the height of the surface represents the value JB. So the height هنا هي cost function. Okay, and it represents a certain point. Okay, what we want to do really is to find the value of W and B that corresponds to the minimum of the cost function. So نحن we want to really get this point over here. This point represents the lowest cost function possible. So the higher point we go is the higher cost function, which we don't want. And so we want to go as low as possible, which is here. Okay. This is the lowest point on the graph. We need to always go to the lowest global optimum, which is the lowest point in any graph. And even though the graph the results is not the the lowest, the closest, but we need to get the closest possible. Okay, we need to achieve as good as we can. Even though if the predicted and the actual are far, we need to get them as close as possible. So it turns out that this particular cost function J is a convex function. So it's just a single big ball. You can see here the graph looks like a big ball. This is called a convex function. And the convex function looks something like this. Again, it looks like a big U or a big ball. Okay, and this when we have a convex function, صراحة things get much easier, much simpler because it is very clear for us where the lowest point is. However, we can get sometimes functions that look like this, which are non-convex. بيكونوا هيك. Okay, and you can see home we have a lot of local optimums. Okay, we don't know which one is the global optimum. So for the sake of explaining gradient descent, we're gonna look at the convex one, and there's a huge reason uh, why this is way simpler than the other. And when we have a convex uh, function, things get a little bit simpler. Why? Because here, for example, we can initialize at any particular point. Uh, so we can say we can start over here, we can start over here, we can start over here, or anywhere, or you can start over here. Okay, you can. It doesn't really matter how high or low. Essentially, we're gonna be going down, down, down. However, if you want to start here, okay, if you go down to the deepest hill, you'd go down, and the gradient descent does not really go up. Okay, and this might not be the lowest point. Okay, it might be here. Okay, so you cannot really start at any random point with the non-convex. But since it is a convex uh, function, you can really start anywhere where we want. Okay. Now, random initialization doesn't really work usually on logistic regression, but for the sake of this example, because it is a convex, so you can start wherever you want. Okay. So what does a gradient descent does? It starts at an initial point and takes a step in the steepest downhill direction. So we start wherever we want, and then it checks where is the steepest downhill direction. So it would not only go down like here or here, it would take the steepest down. So it would know it would go down here, okay? And it would stop and it go in direction to this point. And you might end up there because it's trying to take you to the steepest downhill direction, okay, of the steepest descent or as quickly as possible. So we are trying not only to go downwards, we're trying to take the steepest and the quicker way possible to go down. Okay. And so this is only one iteration of the graded descent. And after two iterations of the graded descent, you get lower. So we go get lower and lower and so on. So you could go on a third, fourth, or fifth. It doesn't matter until you eventually converge and you reach a global optimum or something close to the global optimum. So if it is not here, we can reach here or here. It is fine as long as we this is the lowest point. Yani, we reach the very close to the global optimum. Okay, and this is what we want. This is the lowest difference between the y hat and yi. So this picture illustrates the graded descent algorithm. Let us write a little bit more of details on the purpose of illustration. So uh, this might when it looks a bit in a 3D dimensional picture, it might look a bit difficult to understand. But for the purpose of illustration, let's say that there's some function GW here that you want to minimize the function that looks like this. To make this simple, we ignored B for now, so we made it only one dimensional. Okay, and so for the gradient descent, okay, we are going to repeatedly carry out the following update, which is this algorithm. Okay, we take this value W and update it to represent the updating W. So we set here W to W minus alpha, and this is a derivative dW d of JW over dW, and we repeatedly do that until we go to the lowest point or until the algorithm converges. يعني, in other words, until we reach the steepest point or the lowest point of the graph as possible. Okay, so a couple of points in the notation. Here, alpha is the learning rate. Okay, and it controls how big we take a step on each iteration of the gradient descent. We will talk later about some ways of choosing the learning rate, and we will talk on what basis we will choose the learning rate, but this is for later on, so we don't have to worry about this right now. And the second quantity here is the derivative here. Okay, and this basically the change that you want to make on the parameters W. So the derivative is the number that is keeps on changing. And when you implement gradient descent, you will see the variable name in your code as dw and will be used in the representation in the derivative term. So when you write code, you're gonna see something like this. And when you want to check code online, you're gonna see something like this as dw. So when you see dw in your code, this essentially means the derivative that you're trying to achieve. Okay. So we use dw to represent the variable name of the derivative. And let's now make sure that this gradient descent update makes sense. So let's take w. Let's say that w was over here. Okay. And again, it could be at any point. Okay. And if w is over here, then that means jw is over here. Okay. And remember that the definition of the derivative is the slope of a function at the point. So the slope of the function is really the height divided the width right to the lower triangle. Okay. So if the point is here, okay, here is the triangle of JW. Look, if you want to go to this point, it would look like here. So we have this triangle, and this triangle is the slope. Okay, and so here the derivative is positive. W gets updated, okay, as W minus the learning rate times the derivative is positive. So we end up subtracting W and we end up taking a step to the left again. So we take a step to the left again. And since the derivative is still positive, okay, this would make the gradient descent, your algorithm slowly decreasing the parameter. So we keep going down and down and down. Okay, and if you have started off with this large value of w, okay, it would go keep going down. And so it does not really matter where you start from. Okay, and another example is if w over here was on the other side. So let's say it started here. Okay, and then at this point, the slope here of djw would be negative. So uh, here djw over dw would be negative. Okay, and so the gradient would send an update by subtracting alpha times a negative number, and so end up slowly increasing w. So you're making w bigger and bigger with successive generation of gradient descents. So if you go down, w is just getting bigger and bigger because we started at a negative point. But this doesn't really matter, okay, as long as we reach the lowest point. So hopefully, whether you initialize on the left or the right, you will end up moving towards the central global minimum. Okay, and the global minimum that we can obviously see and we can all agree is right over almost here. Okay, and this is where the graph is trying to reach. Okay, or gradient descent is trying to achieve. And if you're unfamiliar with derivatives, don't worry. You don't need to have a deep calculus knowledge on how it works, and but if you have of understanding of derivatives, it would really help you on how things are working and have a deeper understanding of derivatives. But for now, what we need to know that dgw over dw represents the slope of the function, and we want the slope of the function at the current setting parameters, so we can find the steepest descent, so that we know which direction we need to step on. Okay, in order to go downhill on the cost j, so we just need to know where we are, so we can keep on going downhill. Okay. And this is basically how gradient descent work. But now let's jump a little bit to derivatives. And I want to get a deeper intuitive understanding of calculus and derivatives, because even though you don't need a deep understanding of calculus in order to apply neural network and deep learning very effectively, we need these kind of calculus and derivatives to make functions that are called forward propagation and backward propagation, that we learn about very soon. Okay, and I'll just give a few examples to get an intuitive understanding for this in order to build a successfully and apply the algorithms. Okay, so I have plotted here a function f of a which is equals to 3a. It's just a straight line, and really with deep learning you're not gonna find a straight line. Okay, we will find convex functions, some very complex functions and graphs. Okay, but for the sake of understanding, we will take this kind of line. We'll take this kind of example to test it on. So let's take a few points on this function. Okay. Let's say a is equals to 2. Okay. A is equals to 2. And when a is equals to 2, we know that f of a is 3 times 2, which will be 6. Okay. And if you now give a little, okay, so let's first graph this. Let's put 2 here. So this is not to scale, this is just to understand it. So this might not be a very accurate graph, but for the sake of understanding. Okay, let's say 2 is here and 6, 2 is here, 6 is here. And we everybody has took this basically in high school on how to graph it, so it is pretty straightforward. Okay. Now, what happens if we take a little bit a nudge to the right? So if we move a little bit to the right, so we say a is equals to 2.001. And when a is 2.001, okay, we see f of a is gonna be equals to 6.003. And let's plot it here. Okay. Um, so if you look at this little triangle, I'm gonna draw right now. Okay, 1 second. Let me get the pen. Let's make it a different color. Okay. So if you look at this triangle here, it's a perfect triangle. Okay, you would see that okay, you'd see that the nudge 0.01 to the right of A goes up by 0.03. So here we went 0.01, 0.01, and it goes up 0.003. Okay. And the amount that f of A went up is 3 times as big as the amount I nudged A to the right. And we are going to say that the slope or the derivative of function f of A, when A is equals to 2, then the slope is 3. So let me change the color. So when the slope or derivative is equals to of A at A equals to 2, then the slope is 3. Okay. The term derivative just basically means slope. Okay. So, but the derivative really sounds a bit scarier or fancier name. So whenever you hear of derivative, it's literally just think slope. Okay. This will help you really understand of why we're doing derivatives at not just only for gradient descent, for anything really. Okay. But more formally, slope is the definition of height. So let's say here slope is height over width. Okay. As you can see from the little triangle that we have here. So if you see here, 0.003 over 0.001, we will have 3. Okay. And the fact that the slope or the derivative is equals to 3 just represents that the fact that when you nudge A here from a little bit to the right by any amount, then f of A goes up by 3 times. Uh, it goes by 3 times the amount that you nudge it by. So it doesn't matter if you take 2 and 6, but the difference between these 2 points will always be the 3 times. Um, and- okay, so so all the slope of A is uh, it's the derivative. So now let's take a different a different example. And let's say A is equals to 3, A is equals to 5. that would mean f of a would be 15. And when a is equals to, if we nudge a little bit, and we make it, we nudge a by 0.01, make a 0.001, then we can see f of a, it would be 0.003. Okay. And so the slope again, at no matter what point it is gonna be 3. And the way we write this is that the slope of function f is equals to 3. So the way we write this is like this. D of f of a is of or over dA is going to be 3. And we say and here, yeah, okay. So all this equation means is that if I set a number, then I expect f of a to go up by 3 times as much as I nudge the value of a. Okay, and the formal definition uh, of is not only moving the number by 0.01. Okay, so derivatives does not only move the number by 0.01, but by extremely way more than that. Okay, and it would be way less than 0.0. It could be zero. It is such an extreme number, so it's less than 0.0000000.1, and no matter what, the number, okay, would always be 3. Okay, so derivatives take such a small nudge to the right. It is infinitely less than 0.01, and it would always be a 3. So this is what really the derivative actually mean. But for the purpose of understanding, I just took 0.01. Okay, and now one property of derivative is that no matter where you take the slope, the function, okay, will always be 3. So, but usually the numbers are very small, a very small nudge to the right, and we don't really care about the big numbers right now. And this is just an example for a straight line. But what if we took like a convex function? So let's say x squared. Okay, so if we have here x squared, okay, let's just take this side. Okay, and call this x squared. Okay, and we took here a is equals to 2. Okay, let's say 2 is here. Okay, then f of a will be 4. Okay, and if a is 2.001, f of a would be, just give me a second. Let me get a calculator for this. And it would be um, 4.004001. Okay, so if you nudge it to the right, 1, it would be 4.004. And you can see here the triangle would always go up by 2x times. Okay, because we know that the derivative of x squared is gonna be 2x. Okay, and if no matter what point is that, so if we take the point here, you can see it is converging. It's going down and down and down. So that's why the straight line is a bit simpler than uh, the an x squared or different types of graphs. But for the sake of example, I hope this clears why we're using derivatives. Okay, so we're using derivatives because we want to check the point from one point to another when we move it, and we need to take the steepest downhill. So when we want to go down, we want to see is the number changing? Is it going lower and lower? So it started here at 4.001, goes to 4, and you need to keep going down and down until the number is very close to converging, or the lowest number that we can reach. Okay, and the derivative of a function, just again, what I want you to take from this is that the derivative of the function just means the slope of the function, and the slope of the function can be different points of the function. So the slope or the derivative can be at different points on the curve. And the takeaway is that for now, if you don't know derivatives very much, derivatives are just slopes. And if you're not really good with the derivatives, it is okay. We don't really need to solve very complex derivatives for you to really implement neural networks. And you can get the solutions of the derivative anywhere online, or we have so many calculators online to find you the derivative, the function. So I don't really care if you know how. I don't really want you to know very good derivatives. I just need you to know the understanding and why we're using derivatives, or why we're using slopes to find the gradient descent. Why we use it in the gradient descent, and and especially okay when we want to find the lowest global optimum. Okay, so this is it for the derivatives. Okay, now we're going to talk a bit about the computational graph. Um, as you've heard me say before a lot, that the computation of a neural network are organized in terms of forward propagation step, and we compute the output of the neural network followed by a backward propagation step, which we use to compute the gradient or the derivatives. So the computation graph explains why is it organized this way. And in order to illustrate the computation graph, let's use a simpler example than logistic regression for a full neural network. Okay, so let's say we're trying to compute a function j with three variables. Okay, so let's say j has three variables, a, b, and c. Okay, and let's say the function is 3a plus bc. Okay, and computing this function has three distinct steps. Okay, so this is a very simple um, function that you might see, and really anyone can solve it easily. But I want to show you how a computational graph behaves. Okay, and this is how a neural network essentially behaves. So the first, you need to compute what is BC. Okay, so let's say we store that in a variable called u. We put u is equals to bc, or b times c, and then you might compute what is a plus bc. Okay, and we can say that v stored in a value v, okay, is a plus u, as we can see here, u is. Okay, and then finally, your output j, okay, would be 3 times v. Okay, and we can take these steps and draw them into a computational problem. So you can see that this is here u, and this is here is v, and all of this is j. Okay, and we can take these three sets and draw them into a computational graph. So when you see a computational graph, it's going to be looking something like this. So let's say we have A, B, and C. So the first thing that we need to do is compute U, and U is equals to B times C. So we can say that here U is B times C, okay? And we need to have two inputs to solve this. We need an input C and input B. And then you might want to compute V, and V is equals to A plus U. So you would say here V is equals to A plus U, okay, which also takes two inputs. It takes inputs U that we got from here, and it takes an input A, which we have over there. And so then we have an example um, to find J. J is equals to 3V. Okay, so let's take an example. Let's assume A is equals to 5. Okay, and B is equals to 3, and C is equals to 2. And when A is equals to 5 and 3 is equals to 2, we can solve the formula right now. So this would be 3 times 2 would be 6. Okay, and A plus 6 plus 5 would be 11. Okay, and 11 times 3 would be 33. And we can verify this, okay, by computing the original formula over here. So you can see that 3, sorry, 3, 6, sorry, 1 second. Let me make this clear. Three plus 5 plus uh okay, 3 times 2. Okay, we would have 33. Okay, so the computational graph comes in handy when when there is some distinguished or some special variables, such as J, in this case that you want to optimize. And in the case of logistic regression, J is of course the cost function. Okay, it is not as simple as 3A plus BC. Okay, and we are trying to minimize that cost function. And what we are seeing in this little example is through a left to right pass. So we see we went from here to here, then from here to here. This is going from left to right. Okay, and you can compute the value of J, and you will see that the next couple, like soon, okay, since the time is a bit tight now, we will see soon that in order to compute derivatives, you will need a right to left pass. So if we were computing derivatives, we would need a backward propagation. We would go from here and here to find the derivative and to calculate the derivatives. And going on the opposite direction, that would be how derivatives are computed. Okay. So to recap, uh, the computation graph organizes a computation, okay, from left to right. Okay, while computing derivatives, we will do that through a backward propagation from right to left. So let me draw this in blue to be better. So when you want to compute derivatives, okay, it would go through a backward propagation, okay, step. Uh, and this is really essential when we want to compute derivatives. It cannot really work another way. It's called from a right to left or a backward propagation pass. And if we want to compute a normal computation, okay, then it would be something along the left to right arrows, okay, which would be a password or a forward propagation step, okay, and this is basically it for today. We will talk later about more complex computation graphs and how it looks with derivatives. Okay, but I hope you got a good understanding of what is a computational graph, when do we use backward and forward propagation, and how a computational graph looks like. This is this is it. Okay, this is how usually a computational graph looks like. It's a very simple for now. It's only three stages. Okay, but it could be more complex or more than three steps. Okay, but I'm trying to keep it as simple as possible so you can really understand. And then when you see the difficult and the really hard numbers, you'd at least know what and how the process is going through. And the numbers or the maths or the computation and the derivatives might get really in the way of understanding some couple concepts. So that's why I'm going through a simple maths and simple derivatives to really give you this kind of understanding of how a neural network is going on and how it's working. So I hope it's clear, and I'll see you hopefully next week. Thank you.